Here's another example. Consider the set P sub 2 of polynomials with coefficients from the set of real numbers of degree at most 2 together with a zero polynomial. So the polynomial with zero coefficient. Now, let's endow P sub 2 with the following operations, O plus and O times. Okay. Then, with these operations, P sub 2 becomes a vector space. And we note that the operations O plus and O times that we defined are nothing but addition of polynomials and multiplication of polynomials respectively. Well, here we are multiplying the polynomial at squared plus bt plus c with the constant polynomial r. Okay. So to check that P sub 2 is indeed a vector space, let's verify each condition in the definition. So if you take two polynomials fg, the degree of f and g are the degrees of f and g are both at most 2. So if we take the sum, the degree of f plus g is also at most 2 or 0. So that tells us that f plus g is in P2. So P2 is closed under the operation of polynomial addition. For all fg in P2, we have this equality, meaning addition of polynomials is commutative, because when we perform addition of polynomials, we are just adding coefficients. But addition of coefficients is simply addition of real numbers, which is a commutative operation. The same is true for condition B. This time we apply the associativity of real numbers. Okay. What is the additive identity in P2? So in P2, we have the zero polynomial denoted by z of t. The coefficients are 0. And if we add z of t to any polynomial, by definition, the result is the polynomial. Okay? Z of t plus f of t equals f of t for any f of t in P2. So we have an additive identity in P2. The additive inverse for a polynomial f in P2, say with coefficients a, b, c, is the polynomial denoted by negative f of t, whose coefficients are negative a, negative b, negative c, respectively. So you can check by the definition of addition that f of t plus this negative f of t will give you the zero polynomial in condition C. Okay, so the first 5 conditions are satisfied. Let's look at the conditions relative to multiplication. So for any element f in P2 and any real number c, from the definition, Cf of t will have degree at most 2 as well for the zero polynomial. But in any case, Cf of t is in P2. Okay, so P2 is closed under multiplication or scalar multiplication. For any fg in P2 and any real number c, the distributive property of scalar multiplication over vector addition is satisfied because we are just performing multiplication with real numbers and addition with real numbers on the coefficients. So this is satisfied. And the same reasoning is applied, no, for condition f. So we can distribute f of t to the summands here, but note again that the summands here are scalars, no? They are real numbers. And well, scalar multiplication is compatible with multiplication of real numbers because when we perform scalar multiplication, we're just multiplying real numbers. So compatibility follows. And finally, it's easy to see that if we multiply 1 by f of t, the result is always f of t for any polynomial f of t in P2. So this completes, no, the verification for P2. P2 is a vector space. In fact, we can generalize the observation in example 3. In general, if n is a positive integer, and we consider the set Pn of polynomials with coefficients in the set of real numbers of degree at most n, together with the zero polynomial, then if we define on Pn a similar set of operations plus and times, which are nothing but addition of polynomials and multiplication of a polynomial by a constant polynomial, then P sub n is a vector space. Okay. So the justification is the same as in example 3. So we're not going to repeat it. And another interesting example is the set script f of all continuous functions defined on R, which are real valued, with the following operations. So this is just addition of functions. This is just addition of a function. This is just addition of functions, while this is just multiplication of a function by a constant, or multiplication of a function by a constant function. Okay. So this is a real vector space, and the verification is left to you. It's an exercise. No? It's item 1 in GYHD4. What I want to note here is that the P sub n's in example 4 are subsets of this script f. So all polynomials, no, belong to this family because polynomials are continuous. But there are also non-polynomial vectors, no, in script f. This include the sine function, the cosine function, the natural exponential function, and so on. Okay, so it's a very vast family of vectors. So here we list some properties of vector space. So given a vector space V, the scalar product, no, of any vector with the scalar 0, the real number 0, is always the 0 vector, no, in V. Okay, so note that in the left hand side we are dealing with the 0 scalar, in the right hand side we are dealing with the 0 vector. Similarly, the scalar product of any scalar C with the 0 vector will always result to the 0 vector. So in a vector space, we have this familiar property that if you multiply two quantities and the result is 0, then either factor should be 0. But we should be specific here, no? Because here we are multiplying a scalar with a vector. Okay, so if the scalar multiple of u by c is the 0 vector, then one of them must be 0. So this is either the 0 vector, or rather, this is the 0 scalar, or this is the 0 vector. Okay. And finally, the negative of a vector u should be the same as the scalar multiple of vector u by negative 1. Okay. So to prove that something is a vector space, we have to check that the 10 conditions in the definition are satisfied. But to show that something is not a vector space, it's enough to show that there's at least one condition in the definition that is not satisfied. Alternatively, we can prove that something is not a vector space by showing that any one of these 4 conditions is not satisfied. So let's consider some examples, or rather non-examples of a vector space. First, suppose or consider R2. So the set of all ordered pairs of real numbers, and on R2, instead of defining the usual vector addition and scalar multiplication, we endow R2 with the usual vector addition and a different scalar multiplication. Okay, so for this scalar multiplication, what we do is we just multiply the second component by the scalar and leave the first component fixed. So this is not a vector space because property 4 above is not satisfied. That property has something to do with the negative of a vector. So if it is a vector space, then under this condition, by property 4, the negative of xy should be x negative y. Okay, so this is the negative of xy, then x negative y should be the same as the vector with components negative x negative y. Okay. So these two vectors must be the same. So here we are applying the uniqueness of the negative of a vector. So this is one negative, this is another negative, but the negative of a vector is unique, so they must be the same. But equality of vectors means equality of respective components. Okay, so x must be equal to negative x, negative y equals negative y for any xy, because xy is arbitrary. And the first equality is absurd, no? If you take x to be a non-zero real number. So this contradiction tells us that this R2 together with these operations will not make a vector space. So here's another example. So here we use the notation, no, in algebra or in elementary calculus. Consider R3 and endow R3 with operations O plus and O times as shown. O plus is, as again, the usual addition of vectors, no? But this time, scalar multiplication is defined in the following sense. So for scalar C, CO times XYZ is the vector with second component 1, first and third components are unchanged. Okay. So this is also not a vector space because property 1 is not satisfied. So this has something to do with the with multiplying a vector by the zero scalar. Okay. So if this is a vector space, then it should satisfy property 1. No? But if we take C equals 0 and we take any vector xyz, the definition of scalar multiplication here tells us that this equals this vector with second component 1. Okay, so this should be the zero vector according to property 1 if we assume that this is a vector space. But the zero vector must be unique. So this vector must be the same as the vector with components 0, 0, 0. And this equality of vectors is clearly absurd. Just look at the second components. So this verifies that the set we are talking about with operations O plus and O times is not a vector space.